Good morning, ladies and gentlemen. It is my privilege to welcome you all to the second technical session on the day 2 of the 15th International Research Conference of General Sir John Kothalavala Defence University. You are here with us in the engineering session conducted on the theme of economic revival, national security, and sustainability through advancement of science, technology, and innovation. This session will be chaired by Air Vice Marshal LMSK Leelaratne, retired, while the reporter will be Lady Officer Cadet AMBI Adhikari. Now, I would like to invite Air Vice Marshal LMSK Leelaratne, retired, to the head table. I would also like to invite all the authors who are presenting in this session and the reporter to the head table. Thank you. Ladies and gentlemen, I have the honor of giving a brief introduction of the chairperson of this session, Air Vice Marshal LMSK Leelaratne. Air Vice Marshal Kithsiri Leelaratne is an elite alumnus of the General Sir John Kothalavala Defence University. He joined the Sri Lanka Air Force in the year 1988 and graduated with a bachelor's degree in engineering. He also completed his master's in Defense and Strategic Studies from the KDU and completed his senior air staff course in Bangladesh. He also holds postgraduate qualifications in aircraft armament, technology from the US, aeronautical engineering from India, human resource management, and quality management from Sri Lanka. During his illustrious career in the Sri Lanka Air Force in the capacity of an engineer, he has worked extensively on fighter jets and served in several prestigious appointments, including Officer Commanding Maintenance of No. 14 Squadron, Commanding Officer Aircraft Engineering Support Wing, Staff Officer to the Director of General Engineering, Command Armament Officer, Command Quality Assurance Officer at Air Force Headquarters, and Staff Officer Technical to the Commander of the Air Force at the Sri Lanka Air Force Headquarters. Ultimately, he served as the Air Secretary at Air Force Headquarters and the Director Provost at Air Force Headquarters prior to his retirement. He possessed a wealth of experience in the military engineering field and has received specialized overseas training in aircraft armament, guided weapons, and ejection seats. He has served his alma mater as a visiting lecturer since 1999. He also conducts visiting lectures on aircraft armament and weapons technology to higher education institutions in the military. Now, I would like to thank you, sir. Also, welcome, VC, sir. An elite sportsman, Air Vice Marshal LMSK Leelaratne, retired, is also the Secretary General in the Cycling Federation of Sri Lanka. Now, I cordially call upon Air Vice Marshal LMSK Leelaratne, retired, to chair the session. Over to you, sir.
Thank you very much for the lovely introduction. So, may I start, sir? Thank you very much, sir. Good morning, VC, sir, senior professors, Dean, Faculty of Engineering, all staff members, ladies and gentlemen. Once again, good morning to you all. First of all, I would like to thank Vice Chancellor of Sir John Kothalavala Defence University inviting me as to chair the session of technical session for the third time. So this is very rare opportunity as an engineering officer get from the Sri Lanka Air Force. So I am so lucky to have sir for the third time. So we know that I don't want to explain the vast areas covered by this university. So one of all students, the main aim of this exercise is to present their papers very effectively, to utilize, you minimize or whatever the resources available through the KDU, and to present to nation their capabilities and whatever the new innovatives. Today there are 4 researchers. They are going to conduct these research papers. First topic is Thermographic inspection system for surface coating defects in aircraft fuselage. So all 4 subjects regarding these 4 topics related to the aircraft maintenance. So if I talk about the 2 authors about them, WPMY Thilakarathna, Miss WPM Thilakarathna completed the undergraduate academic program in the field of mechatronic engineering from General Sir John Kothala Defense University, and is waiting for the graduation. Currently working as a temporary instructor at KDU. Her research interests include mechanical designing, control system, and robotics. Regarding Mr. Ziyard, the other author, complete the undergraduate academic program in the field of mechatronics, engineering from KDU, and waiting for graduation again. Currently working as an executive automation engineering at Marshal. Sri Lanka, his research interests include machine design in automobile and robotics. So before the subject, I would like to give small introduction about the thermographic inspection systems. This is very special topic related to Sri Lankan context. Now we are doing the very all type of inspection system in the fuselage, identifying defects. Surface coating on the aircraft protect the skin of the aircraft from external damage due to corrosion, and it also reduces the friction between air and the surface, making them vital for aircraft operations. These coatings are prone to damage through various debris that also includes bird strikes. Damage to the surface coating will result in corrosion, damage the skin surface, and prolonged exposure to the elements, if unnoticed, and create catastrophic failure of the skin, which may result even in a crash of aircraft. To arrest this possibility, the manufacturers have detailed inspection procedure to inspect surface damages of aircraft skin. The first step would be identify damages to surface coating by way of visual inspection, and subsequent procedure of incorporating NDT methods such as ultrasonic, MPI, and X-ray to determine extent of surface damage. These procedures are time-consuming and makes aircraft grounding time for maintenance longer. In addition to experience of an inspector is a key component in the identify probable damages as same as not easy to spot visually. The first research presented today by his team introduced an innovative technology to make this inspection much easier and cost-effective. They have researched the possibility of using thermal imaging technology, and by analyzing the same through means of purpose-made software package to highlight the possible areas of damage to the surface coating. The team has concluded that by following this method and application of the technology presented efficiency, surface inspection could be increased up to by 9.25%. That is a huge margin. Further, same will also minimize the inherent disadvantages. So further ado, I would like to invite 2 authors to present their papers. Or to you.
Good morning, ladies and gentlemen. I'm Adil Ziyard. It's an honor to be presenting you with our research study along with my colleague Monisha Thilakarathna. Our research study was conducted on the use of a thermographic inspection system for detecting surface coating defects on an aircraft. Firstly, our presentation today will proceed according to the following content. To start off, I will be giving you a brief introduction to the purpose of our research and how we were inspired to conduct it. When we consider an aircraft, protection towards its operating environment is very important. An aircraft's outer shell is protected from corrosion and deterioration using a surface coating. The effects of a damaged coating on the safety of the outer shell could lead to fatigue crack formation in extreme cases. The main causes of surface coating damage are impacts by particles, debris, and bird strikes. This highlights the role of preventive maintenance of the surface coating on an aircraft. So this brings us to the motivation to conduct our research study. The following are the key points for our motivation: realizing the importance of frequent successful testing and maintenance of an aircraft's corrosion-resistant coating, identifying the inefficiencies in manual visual inspection and the presence of alternate methods, recent popularity in thermographic inspection systems in the aeronautical industry, identifying the opportunity to advance and improve on non-destructive testing techniques using automation. Finally, the drawback identification of the existing thermographic inspection systems. To analyze the feasibility and the scope of our research study, we visited the Iceman Technical Center and attended a seminar on non-destructive testing done by the Sri Lankan Navy. This led us to confirm that damages to a surface coating are visible on a thermographic image. To investigate what aircraft to base our system on, we visited the Air Support Wing of the Sri Lankan Air Force, where the PT-06 aircraft was selected. This slide shows the analysis on existing thermographic inspection systems where aircraft outer shells are inspected by a person with a thermographic camera. The person needs to be knowledgeable enough to identify abnormalities, be consistent and on focus for extended periods of time. Moving on to finalizing our scope of the study, the aim of our research study was constrained to successfully designing an automated system that can test for surface coating defects on a scaled down aircraft fuselage using non-contact, non-destructive infrared thermography and proving its effectiveness against the norm. Our objectives were as follows.
Moving on to the methodology, according to the finalized objectives, we prepared a methodology to successfully complete our research. To complete first objective, which was to design a scaled-down system, there were 5 distinct steps: develop conceptual design, selection of materials, design calculation and model the design. Next step was to develop processing algorithm and motor controlling. And the final steps were to fabricate and test. Then we move on to the design considerations. As the first step of methodology, we developed a conceptual design, and best suitable design was selected based upon the design table with concise rating table. And here you can see the final design of the system was basically with 4 subsystems: rover, lifting mechanism, thermal imaging system and control system. Lifting mechanism was with 2 linear drives, and the thermal imaging system was with tilting mechanism and a camera assembly. This is the final 3D design of the system, which was modeled using SolidWorks software. For this system design, all the proportions were based on PT-6 aircraft, and the total area coverage for one static placement of the system. This is the camera lifting mechanism, and here you have the camera tilting mechanism and the camera setup and the trolley and the control panel and the control box. Lifting mechanism, which is the main subsystem. It's a double-axis gantry consists with two linear drives which are driven by stepper motors, and the basic purpose of this mechanism was to carry the camera for scanning. Next, the second subsystem, thermal imaging system. There were mainly two parts in the thermal imaging system. Tilting mechanism to make sure that the camera is perpendicular to the surface, and the camera assembly with FLIR Lepton 3 thermal camera. The control system had two subsystems which were controlled by two different controllers. Controller 1, Raspberry Pi, to control the image capturing and processing. Controller 2, Arduino Mega, for controlling lifting and tilting mechanism. For the controlling part, we need to identify the movement of lifting and tilting mechanism. Here you can see the path of the scanning system. And this is the control circuit of lifting mechanism.
Moving on to the thermal image processing system, we installed the operating system on our Raspberry Pi controller and installed all software dependencies for the thermal camera software that we used. Then we formulated the thermal image dataset creation and its analysis according to the following steps. We obtained 70 thermal images, including a spectrum of very different conditions, and then we manipulated them to make 560 images. Filters were then applied to enhance the images. In the end, we realized that machine learning was not the best technique in our case, and instead it was better to use image segmentation. This slide shows the initial thermal data set we obtained. This slide shows the total data set that we used for testing. The total data set was created by manipulating the original 70 images. This slide shows the results for the main filters we applied to enhance the images. We applied two image segmentation techniques to compare them. The triangle thresholding technique and Otsu's thresholding technique were analyzed, and the results were used to conclude the best thresholding technique, which was triangle method coupled with subtraction arithmetic filtering. This slide shows the control algorithm we used for the detection of surface defects. Firstly, the operator presses the start button, which is read by the Arduino as an input signal. Then the Arduino controls the camera positioning system to position it at the correct place. Then after it is placed correctly, the Raspberry Pi detects that and then proceeds with the image capturing and then the image processing, and then indicates to the operator whether a defect is present or not. Next, we move on to the fabrication part, which we proceeded with 3 phases. The first phase, the fabrication of the parts. The second phase, the fabrication of the sub-assemblies. And the third phase, the finalizing of all the parts and sub-assemblies together. This video shows the operation of our equipment. Unfortunately, we were unable to test the equipment on an actual aircraft due to COVID restrictions during our research. So this demonstration will just give a brief idea on it. For the purpose of this demonstration, we have simplified.
During the completion of system, each subpart, double axis gantry, tilting mechanism, image processing system was tested segment-wise prior to finalizing the design. Specifically considering the image processing system, different conditions that the thermal camera would be possibly encounter, such as low light conditions, high exposure and shadow on surface conditions were explored. And a stock camera image with defect was analyzed using the same condition to justify the use of thermal camera instead of a normal camera. The two types of threshold segmentation methods were compared to confirm the system applicability. It was observed that the triangle method was better than the obtuse method due to its effectively defining the foreground to the defect area since it brought less amount of noise. And this figure shows the comparison of two thresholding methods and the noise appearance. After fully analyzing the source data set, we were able to identify the pixel count range for defect image is between 11 to 108 90 pixels. Finalized system was able to cover the total area of 16,200 square centimeters per one static placement of the system. Compared to the manual inspection, total time taken for inspection procedure for one static placement, this system was obtained 18 minutes and 55 seconds, whereas the manual inspection took 20 minutes. Thereby, from this system, we were able to increase the overall efficiency by 9.25. In conclusion, this prototype was developed to introduce a novel concept to the surface coating defect detection in aircraft and to overcome the drawbacks of existing manual inspection methods. First two objectives, which was to design a scaled down system for obtaining thermal image and process the image, were successfully completed through camera lifting mechanism and image processing system. Defect indication panel was there to complete the second objective, which was to develop a method that can indicate the operator. Finally, with the automated surface defect indication mechanism, we were able to reduce worker involvement and the total time required for manual inspection. This research continued on improving image processing system with machine learning algorithm, and further research need to be done to improve the system design with automated navigation system and IoT-based indication system. The references that we have used throughout our research are given here. And finally, we want to give our sincere gratitude to our university and Department of Mechanical Engineering and the head of the Department of Aeronautical Engineering and our instructors and all our parents and siblings. Thank you.
Thank you very much. That was a very nice research done by two authors, especially regarding the present day requirement. That was a very innovative thing you have, if you can implement, especially that we have to check that one.
Yes.
So practically. Sir, now we would like to take this session for Q&A. If you have any questions or if you want to clarify anything regarding this research, you can ask. We have 2 minutes.
Thank you. Thank you so much. For the first time, I came to know that the thermographic image can be used to study the surface morphology of any paint surface. Maybe with this, now we can check whether there is indent or something unusual thing on the surface. But I wonder when because it is a IR based camera, if the temperature of the surface increased, so are there any method to normalize the other points?
We've developed this prototype using the assumption that this testing will be carried out inside a hangar. So by the time the aircraft lands and gets into a hangar, we assume that the temperature will be around 35 degrees Celsius, which is the temperature that we have obtained our image data set.
Okay, thank you so much.
Thank you.
You said the machine learning, you use one algorithm. Can I know the algorithm you used?
So we didn't use a machine learning algorithm here, but what we did was we checked whether we should use the machine learning algorithm or whether we should use another algorithm to do it. So when we checked that, we realized that this particular application will only have two classifications, no defect and defect. So we realized that in the machine learning algorithm, using a machine learning algorithm will be more complex, and with our project time constraints, it will be better for us to invest our time in other things rather than here. So we went with the image segmentation.
Okay, since you are going to develop this further, let me propose that machine learning should not be used for this type of applications. I think it is the deep learning you have to use. And as you have well cited in your second reference, they have also used the deep learning. I think deep learning is the best method for this type of application. So I'm just giving a proposal for further improvement.
Thank you very much, sir. We'll look into that.
Okay. As an aeronautical engineer, first I would like to congratulate you all at what you have done at undergraduate level. Congratulations to you. Again, as an aircraft maintenance engineer who have been in the industry, there are certain concerns that I have. I would like to add them, which would add more value to your presentation. So that first thing is, when you take an aircraft, there are different contours because it's not a flat surface. So that I think you'll have to take into consideration. And when you're looking at the lateral and the movement of the scanning process, once again, it's not equivalent. So that also you will have to take into consideration. So in future research, that would be highly beneficial. And also a practical aspect that I would like to add, when you're looking at the surface of the aircraft, the number of coatings and paints that we have is not identical. So that again is because unlike in the commercial aircraft, especially in the military context, there are several coatings in there. So if you can add all these value additions, I think then this would be a very good idea. And I really would like to congratulate and try to test it on the aircraft. That would give you more insights to develop that. Thank you.
Thank you very much, sir.
That is last question.
Thank you for your informative presentation. My question is going towards the thermographic imaging that can be used in detecting surface cracks on helicopter blades. So like you are using this to identify the surface defects in paint, can you improve it to identify surface defects in helicopter blades? Because especially we are still using very inferior methods like tapping tests. So this can be very useful in that field.
Thank you, sir. So when we visited the Iceman Technical Center during the verification stages of our research, we tried to use their very concise equipment to check whether we can detect the surface cracks. And unfortunately, because the IR waves are being used here, the small cracks, that is the minute cracks on a surface, is not able to be detected just through thermographic inspection. So what I propose is we may be able to couple the thermographic inspection with say ultrasonic testing, so that it will go hand in hand and you'll be able to get the desired output that you want.
Thank you.
Yeah, Niroshan, if I add one thing to more, that is basically helicopters, rotor blades. That is especially this thermographic inspection, they are planned to design for the honeycomb structures. So especially water intrusion, to check that one. So that is the good idea for that one. Okay, sir, thank you very much then. That was a very nice presenter and that good Q&A session. You can see.
Thank you very much.
Thank you.
So our second topic today is going to be, that is also another very interesting aerodynamics topic, estimation of lift hysteresis of an airfoil in a low speed flow. So there are two, author is Mr. WRD Jayathilake. He is an undergraduate at the Department of Aeronautical Engineering at the Faculty of Engineering of Sir John Kothalawa Defence University. So regarding this topic, I think that is also very interesting one, and especially regarding the today's context, the unmanned aerial vehicle. The study of the properties of moving air and interaction between the air and solid bodies moving through its defined as the aerodynamics. It is one of the principal subjects that undergraduates of aeronautical engineering are supposed to undergo. Lift hysteresis of an airfoil is a phenomenon leads to difference, separation, and reattachment angle of airfoil at an angle of attack near and above stall. This occurs when there is a difference in the lift distribution of an airfoil than expected for a given angle of attack when recovering from a stall. This leads to asymmetric flow parameters around body even when boundaries remain symmetric. These advanced aerodynamics phenomena, such as lift hysteresis of an airfoil, are necessarily required to be understood by the aeronautical engineers in order to design airframe structures or to estimate performance parameters of existing airframes. The interest on low-speed flows has been increased lately due to the increased application of unmanned aerial vehicles. The very phenomenon we discussed today, the hysteresis, is difficult to predict due to its inherent physics and extreme sensitivity to the environmental condition. In terms of acoustics, structural, pre-stream turbulence distributions. The research we present today will be based on the research undertaken by Mr. Jayathilake and supervised by J.I. Abeygoonewardene to enhance to a spectrum of knowledge in this area to study. With that, I would welcome Mr. Author to present your presentation.
Thank you for the introduction, sir. Good morning, distinguished chairperson, senior officers, academic staff, ladies and gentlemen. Our research topic is estimation of lift hysteresis of an airfoil in low speed flow. So the outline of our presentation is as shown on the screen. So first, let me give you a brief introduction about what aerodynamic hysteresis is. So sometimes, even though the boundaries might remain symmetric, still when there is large regions of flow separation, this would result in instantaneous and mean flows to be different. So this could lead to hysteresis. Now hysteresis is the forces and the moments which are acting on a body could actually depend on the time history of the attitude. Now as shown in these figures, at a particular angle of attack 14 degrees, the oil flow visualization shows that initially the right wing has a flow separation, and then the left wing has a flow separation. So this has fluctuated, the forces has fluctuated. So moving on, our area of study is static stall hysteresis. So this static stall hysteresis means it refers to the dependency of the current state of the flow on the flow's history of attachment. So to simply put into words, it means for a particular angle of attack, for a particular airfoil, there exists more than one coefficient of lift, drag or moment. As you can see in the figure, the coefficient of as you can see in the figure here, the reattachment point as well as the stalling point has changed because of this hysteresis effect, and also within this hysteresis loop, there's different coefficient of lift values for the same angle of attack. So there are different hysteresis loops. It could either be clockwise hysteresis loop or anti-clockwise hysteresis loop. For the Reynolds number of 150,000, for the Miley, it's an anti-clockwise hysteresis loop, and for the Leelaratne airfoil, it's a clockwise hysteresis loop. So there are various factors affecting the extent of the hysteresis. It could be Reynolds number, turbulence intensity, camber, model imperfections, the flap angle. All of these properties affect to what extent the hysteresis is being made. So why do we study hysteresis? So as I mentioned earlier, there's a difference between the stall and the reattachment point. So assume that the aircraft is flying in the air and the aircraft is stalling when we increase the angle of attack. But now, since the aircraft is stalled, just because we decrease the angle of attack up to the stalling angle that it initially stalled, we cannot have a attached flow. We'll have to further decrease the angle of attack in order to have a reattached flow. Now, so as you can see, these stall conditions and spring flight conditions are being affected by this hysteresis effect. Also, for a given angle of attack and an airfoil, as I mentioned before, the lift coefficient and the lift to drag ratio is different. If we consider the wind turbine blades, because of this hysteresis effect, the blade fatigue is increased, and hence a short operational life will be available. So talking about the existing literature for an experiment conducted on the Leelaratne and the Miley airfoil, it was shown that the increase in the turbulence caused the hysteresis loop to reduce or actually disappear as well if we further increase the turbulence. Also, in one of the tests conducted on a NACA 0018 airfoil, the stall hysteresis loop increased with the Reynolds number, and another test conducted on a NACA 0012 airfoil showed that there was a significant relationship between the difference between the reattachment point and the stalling point on its effective body. So our research is also a continuation of this last point that I mentioned. So moving on to the research objective, what we wanted was to analyze the relationship between the Reynolds number and the static stall hysteresis of an asymmetric airfoil empirically. So as you can see, an airfoil has a physical body as well as an effective body. So actually what the flow sees is not the physical body, but instead it's the effective body. So as you can see here, the smoke wire visualization for a NACA airfoil, we can see that the flow has actually followed a path which is different to its physical body. Also, for lower angles of attack, this is of course not much of a problem because the physical body and the effective body is more or less the same. But for higher angles of attack, when the angle of attack increases, there will be a large wake created, and hence the effective body and the physical body is somewhat different. So as you can see, this is the physical body and the effective body of a NACA 0012 airfoil. There's a drastic difference between these two. So moving on to the methodology. The methodology of our research is as shown on the screen. So we selected an airfoil, the Clark Y14 airfoil. We did the experiments using the Aerolab educational wind tunnel with characteristics mentioned on the screen. We selected the Reynolds number range by considering the characteristics of the wind tunnel, and we got a Reynolds number range of 27,423 to 396,122. And the experiments were conducted for the Reynolds numbers shown on the screen. This is the experimental setup. We mounted the airfoil vertically and we connected it to the liquid manometer. And the pressure variation of the airfoil was measured. The coefficient of pressure was calculated by using this equation. And MATLAB was used in order to calculate the lift curve. And the area between the coefficient of pressure of the lower surface and the upper surface was used in order to find the coefficient of lift. So moving on to the results and discussion. As you can see, this is the CP variation for different Reynolds number. For the Reynolds number of 112,742 is given. Here at 5 degrees, the flow is completely attached. So even though the angle of attack was increasing or decreasing, we have more or less the same variation for the CP. But at 10 degrees, when the within the hysteresis loop, for the increase in angle of attack and for the decrease in angle of attack, the CP variation is somewhat changed, is entirely different from one another. Also at 15 degrees, when the flow is completely separated, the increase in angle of attack and the decrease in angle of attack gives the same, more or less the same results again. So these are the variations, CP variations for the other Reynolds numbers. So moving on to the coefficient of lift variation, as you can see, the hysteresis is being seen here very clearly, and we can see there's a difference in the stall and the reattachment point, and with the increase of the Reynolds number, this hysteresis loop has increased, and again the hysteresis loop has decreased a bit when we increase the Reynolds number further. So moving on to the findings, as I mentioned earlier, at lower Reynolds numbers, at 79,224 Reynolds number and below, we actually did not find any hysteresis loop at these Reynolds numbers. But when we increased the Reynolds numbers, we found there was a really good demonstration of the hysteresis loop. The hysteresis loop was very well visible, and then it increased with the Reynolds number, and at 134,072 Reynolds number, we had the highest hysteresis loop at an angle of 7 degrees. And further, when we increased this Reynolds number, the extent of the hysteresis decreased to 5 degrees. And also the stalling angle, variation of the stalling angle with the Reynolds number, continuously the stalling angle increased with the Reynolds number. So moving on to the limitations of our research, this test was done for a 2D airfoil. Also we had the ability to only vary the angle of attack by multiples of 1 degree. We did this experiment for the incompressible region. The pressure readings were based on the liquid manometer. So whatever the errors associated with the liquid manometer are included in this results, because the time interval also we need to let the pressure readings to settle down before we take any readings in the liquid manometer. Also the human errors while measuring this is also available. So moving on to future work, we expect to carry more internal experiments in order to increase the accuracy of these results, and we'll be conducting CFD simulations to validate these experimental results. And we'll model the effective body of the stalled airfoil, and once we model it, we'll run the CFD simulations for this effective body and determine the relationship between this effective body and the hysteresis loop of the airfoil. So moving on to the conclusion, we studied the effect of Reynolds number on the hysteresis loop, and we found that there were no considerable hysteresis loop observed for low Reynolds numbers, but when the Reynolds number was increased, there was the hysteresis loop was present. and it continued to increase and then again decrease with the Reynolds number. So the extent of the hysteresis loop was actually seen to be dependent on the Reynolds number. So I would, moving on to the acknowledgement, I would like to specially thank the academic and non-academic staff of the Department of Aeronautical Engineering of Faculty of Engineering at General Sir John Kothalaval Defence University. The references that I used are as shown on the screen. Thank you.
Okay. Yeah. Once again, thank you very much, Mr. Jayathilake. You are on time. And that more theories regarding the aerodynamics. If you have any questions or further clarification, you can ask now.
Okay, thank you very much for your nice presentation. And as per your results, it is observed that there's no hysteresis loop at low Reynolds number.
Yes.
Does it due to the resolution of the water manometers in the wind tunnel? Because you have mentioned one of the limitations that you have faced is the water manometers. So have you looked at in that aspect as well, since you did not observe any loop at the low Reynolds number? Any comments on that?
Thank you for the question, sir. Actually, that also is one of the factors that for not having good results for the low Reynolds numbers, because the readings of the pressure liquid manometer was real difficult to read, as I mentioned, because we had to visually read it. But actually at low Reynolds numbers, still there was no any hysteresis loop to be obtained. And I cross-checked with some references as well. Then from those references as well, it was mentioned that for very low Reynolds numbers, and also this depends on the airfoil, the shape of the airfoil as well, hysteresis could not be observed for some airfoils, and also the reason that Sir said was might also be included because there's difficulty in measuring the pressure values as well. But mostly there was no hysteresis to be obtained. Sir.
Right, again, thank you very much for the very interesting research. Now, what I understood was you have developed a correlation between the angle of attack and the Reynolds number in terms of the phenomenon of hysteresis. Now, have you looked at the other factors like the Mach number, the turbulent intensity?
Yes.
Because when there is turbulent intensity, high turbulent intensity, then there is every possibility to have reverse flow. So have you looked at that aspect also?
Sir, now in the wind tunnel at KDU, sir, here there's the turbulence intensity cannot be changed. That's one. And also, sir, the Mach number is not that much of a point to be considered because we are considering the low incompressible regions, sir. And also, as I mentioned in one of the slides, the turbulent intensity actually has an effect on the Reynolds number. When we increase the turbulence intensity, the Reynolds extent of the hysteresis loop actually decreases. But the problem is we do not have the ability to vary the turbulence intensity at our wind tunnel, but we could still increase the surface roughness by maybe attaching some threads or things like that, and maybe we can increase the surface roughness, because the surface roughness is also said to have the same effect similar to that of turbulence intensity. So if we were to increase the turbulence intensity, we could get we could see the change in the hysteresis loops.
What is the critical Reynolds number that you would like to look at in terms of hysteresis? Is there any critical Reynolds number?
Sir, we cannot say that there's a critical Reynolds number for the entire hysteresis to be seen and not seen, sir. It depends on the airfoil and other conditions as well, sir. For this particular airfoil, sir, we could not observe any hysteresis below 79,000 Reynolds number, but we like this might be different for another airfoil because entirely it also depends on the shape, because this depends on the effective body. When the airfoil is tall, there will be an effective body. So when we are decreasing the angle of attack, this effective body will still be intact, and whatever the readings that we are going to get, this effective body will have an influence in them. So this does not, this depends on the shape and the other factors as well, sir.
Thank you.
Okay.
With the temperature, so these turbulence densities might be changed, and the streamline phenomena also might be changed, and the lifting and dragging force also will be changed. In which temperature did you?
Sir, we did this experiment at standard sea level conditions at 28 degrees Celsius, sir.
28.
But yes, sir. But if we were to do this at different temperatures, yes, the results would be different, because even the pressure readings of the manometer would change, sir.
Yeah.
And also the turbulence intensity, and those will be affected, sir.
Yeah. Thank you.
Okay, thank you very much. That was a very interesting, more theory involving presentation, and we can see that you are very conversant with the theories. Thank you very much, Mr. Jayathilake.
Thank you, sir.
Next presentation regarding communications, not the aviation communication, and analysis of impact, technical communication on aviation risk mitigation in the context of aircraft maintenance operation in Sri Lankan context. So, authors, there are two authors. Mr. KMGMWB Samarakoon is a graduate of Department of Aeronautical Engineering at the Faculty of Engineering, General Sir John Kothalawa Defence University. Other one, Mr. SCM Bandara is a graduate of Department of Aeronautical Engineering, Faculty of Engineering of General Sir John Kothalawa Defence University. So this is also another interesting topic, and I think they have done research, not aviation communication, regarding technical communication. So if I add something, it is safe for me to declare that the air travel today is the safest mode of transportation available to public. Although aircraft remains to be fragile piece of equipment, the safety and quality control inputs into the air travel industry in general has made this possible. A key component for keeping the air transportation a safe way to travel is a safety management system, or SMS, undertaken by airline and various stakeholders in this industry. The next paper we are going to discuss today explore the impact of technical communication on aviation risk mitigation in the context of aircraft maintenance operation in Sri Lanka. Technical communication directly affects aviation safety through written and verbal communications, lapses, misunderstanding, language problems, pronunciation, misinterpretation, etc. The situation is more complicated when considering the dynamic environment of flight line maintenance and base maintenance activities, where the fluctuating maintenance demand is to be fulfilled with the limited resources without compensating the quality and standard of the aircraft industry demands. The presenters of this research have undertaken a much needed area of study in Sri Lankan aviation industry, as there are only finite number of empirical research available locally on this subject. After all, we cannot simply apply research done by elsewhere directly to our context, as our ways of communication and understanding of instructions differ from the rest of the world. The research has undertaken by the undergraduates of this university with their instructors, namely Mr. Bandara and Mr. Samarakoon, with the supervising of Dr. Rodrigo. So, gentlemen, now over to you. You can start your presentation.
Good morning, ladies and gentlemen. Today we are going to present an analysis of the impact of technical communication on aviation safety in the context of aircraft maintenance operation in Sri Lanka. This is our content. First, our background. In Sri Lankan aviation industry, we can find only few researchers in under safety management system. Because we are going to do this, what of the reason of that? And we hope to develop the safety management system researchers in Sri Lankan aviation industry. Also, we connect safety management system through the safety promotion. By enhancing safety promotion in Sri Lankan aviation maintenance organizations, we can minimize the rate of accident and incidents. And we want to highlight the direct effects of communication to safety promotion. This is our introduction. This is the ICAO SMS module, Annex 19. These 4 pillars mainly foundation of the SMS. Then we connect with the safety promotion because safety promotion is the most suitable way for doing the researches. And we connect through the SMS safety promotion. Safety promotion connect with the technical communication. Written verbal communication, information understanding, and employee engagement and feedback are the sub-independent variables through the communication. These are our objectives. Develop and highlight the safety management system directives in Sri Lankan aviation industry. Then, to identify the main factors that affect to the safety promotion toward risk mitigation. And also, develop a conceptual framework to know how communication affects the safety promotion toward risk mitigation. This is our methodology. Safety management system, safety promotion, technical communication. These are the main variables, but we have to show how to connect between those things. Then we develop a conceptual framework with sub-independent variables. Written verbal communication, information understanding, and employee engagement and feedback are the sub-independent variables. Then we design the questionnaire-based conceptual framework with Likert scale and collect the data by online. We gather data generally for main organizations with one government organization and 3 private aviation organizations. Then we statically analyze by IBM SPSS software. This is our conceptual framework. The safety promotion connect with communication. The communication is and the safety promotion variable. This is the independent variable. Main independent variable is a communication. Then written verbal communication, information understanding, employee engagement are the sub-independent variable. This is the dependent variable, risk mitigation. I hand over to Chatura to the rest of presentation.
Thank you, Mahen. These are the 3 hypotheses that we developed to conduct our research. And according to these hypotheses, we considered our null hypothesis. These are our results. By analyzing our data, first we get the correlation test. So we use the Pearson correlation to know that there's an adequate relationship between the dependent variable and the independent variables. So we get the values that proper correlate relation range should be -1 to +1. So all the Pearson correlation values are in that acceptable range. And so we can conclude that all the value has the positive strong relationships. And according to that, all hypotheses we can accept because our significant value is less than 0.05. This is the coefficient table we got through the regression analysis. So according to the regression equation, this regression equation we developed. According to that regression equation, if we change one unit in our independent variable, it mentioned that how much of effective on the risk mitigation when keeping other independent variable stays constant. These are the recommendation we got through our research. So through the research finding, safety promotion is main factor to upgrade the safety in Sri Lankan aviation industry. So safety promotion is the most important channel to go through this safety management system. So since most possible way for risk mitigation is to improve safety promotion through sub-variables, by using employee feedback system management can ensure that subordinates could properly understand the communicated information. And also for safe communication, language proficiency of the employees is also very important. And discussion. So in mainly focus in this research to analyze the relationship between safety promotion and risk mitigation through communication. According to our findings, we got that the strong positive correlation between independent variable and the dependent variable. And also for technical understanding about the maintenance information and production planning, information and information understanding and the language proficiency also very important. Conclusion. So we conclude that the written verbal communication, information understanding and employee engagement and feedback have positive impact on risk mitigation towards safety promotion. So using employee feedback system can ensure that subordinates properly understand the communicated information. And according to finding, employee engagement and feedback have highly affected for the risk mitigation towards safety promotion. And also management has to concern about the employee OSH awareness and corrective actions. How did they aware about these corrective and preventive actions, and take effective actions to develop improve the written verbal communication, information understanding and employee engagement and feedback. As limitation, we consider only the line and base maintenance only, and we can develop into the cargo handling departments and ground operation crews. Acknowledgement. We would like to express our deepest appreciation to our supervisor, Dr. WTS Rodrigo, who motivate, advise and encourage us regarding our research. And we would like to extend our sincere gratitude to the Department of Aeronautical Engineering, all academic and non-academic personnel who have helped us all along. Thank you.
Okay, thank you very much, Mr. Samarakoon and Mr. Bandara. You took almost 8 minutes to cover your presentation. So communication is a very important topic in the aviation industry, both aviation communication and the ground communication. They talked about ground communication. So if you have any questions regarding ground communication, you can ask now.
Okay, explain me the issues that you have identified in verbal communication.
Thank you very much for the question, sir. In the verbal communication, with the background, when we have engaged with the line maintenance, with the background noises, some employees don't use the verbal equipment communication. To communicate, they don't use the equipment to communicate in their maintenance practices. That's the main issue we have identified.
In terms of then the communication related to the documents, what are the issues that you have identified?
When the shift handovering, in some private maintenance organization, they don't follow the proper practices. According to that, they don't use proper documentation, and they only use the verbal communication to shift handover, and that will affect to some incident or accidents.
Thank you.
Any questions from the backside? I think no more questions, but that is a very useful topics today's context. Even the communication, due to lack of communication, there are catastrophic failures in the aviation industry. Even they lost aircraft and even passengers, human beings. So that is, thank you very much. Again, Mr. Samarakoon and Mr. Bandara had done good presentation. Thank you.
Thank you very much.
Today's last topic, going to do this topic is an empirical analysis of the impact of aircraft maintenance technical training on risk mitigation in the Sri Lankan aviation industry. So same kind of topic earlier, the risk of technical communication, now technical training. So the two authors, again, Mr. SCM Bandara is a graduate of Department of Aeronautical Engineering at the Faculty of Engineering of General Sir John Kottala Defence University. Another one, KMGMWB Samarakoon, is a graduate of Department of Aeronautical Engineering at the Faculty of Engineering of General Sir John Kottala Defence. Same authors. I will give small introduction about the technical training. This is our last research paper for the day. We have another research undertaken by the same team, I think, same team of the previous paper. We discussed, and their subject is also somewhat similar to the subject we discussed previously. This is an empirical research on the impact on aircraft maintenance training in Sri Lanka on risk mitigation. This is once again, is timely project undertaken by the team of researchers, as there are a lack of empirical research done in Sri Lankan aviation industry. I don't have to emphasize on the importance of safety management system on an airline or related institution towards the safe operation of aircraft. The operational efficiency of aircraft maintenance activities is pivoted on the equilibrium between safety and productivity. Against this backdrop, aviation safety management system play a vital role in ensuring safe operation while enhancing operational efficiency. Aircraft maintenance in-flight activities, maintenance manual, repairing data records, correct procedure, etc., are affected by effective technical training and education. Without proper training and education, aircraft safety will entirely collapse. All modern commercial aircraft associated equipment are highly complicated, and any person who performs maintenance activities on them needs to have a high depth exposure and training, without which it will endanger both safety of the aircraft and passengers who are flying on board. This research discusses each part of this training, and on findings of their empirical research, they will present what parts are more valuable and what emphasis needs to be put on each part of the training. So therefore, once again, I would like to invite Mr. Bandara and Mr. Samarakoon to enlighten us regarding the aviation training, technical training. Thank you.
Thank you. Good morning, ladies and gentlemen. Today we are going to present about an empirical analysis of impact of aircraft maintenance, technical training and education on risk mitigation in the Sri Lankan aviation industry. This is the content we are going to follow through our presentation. Introduction. In a safety management system, we can consider it as a systematic approach to the managed safety. That means that in aviation industry, safety plays a vital role, and also the aviation industry cannot be completely free of hazards and the associated risks. So the purpose of this research is to evaluate the effectiveness on the risk mitigation in the aviation related organization when we change the training and education variables. As the training and education variables, we identified that initial training, continuous training and training resources availability are the most effective factors for risk mitigation. In our research, we have considered the safety management system. According to that, safety management system have main four pillars. In safety promotion is the one main four pillar for the going through the risk mitigation. Research questions. These are the research questions we found that we are going through the research. Here we consider the impact of training and education towards risk mitigation and affecting factors for the risk mitigation. Objectives. These are the objectives we have to carry out in our research. Here, according to our literature review, that there are lack of research conduct on safety promotion and risk mitigation in Sri Lankan aviation industry. So we have to identify the factors affect on risk mitigation towards training and education and evaluate the impact on it. Methodology. So we have done this research as a hypothetic deductive approach based on an empirical review, and also research conduct on a quantitative method. And by developing conceptual framework, we can link the risk mitigation and training education with sub-independent variables as initial training, continuous training and training resource availability. So we have distributed our questionnaire among 200 of employees, and we got 150 feedback to carry out our research. And we analyzed our research by using SPSS. In analysis, we consider the normality, multivariate, correlation and regression. This is the conceptual framework we have developed under safety promotion. Our main variable is training and education. According to that, we link risk mitigation through the initial training, continuous training, training resources availability. I would like to invite Mahen to continue the presentation.
Thank you, Chatura. This is our hypothesis. These hypotheses depend on the initial training, continuous training, training resource availability. Results. First, correlation. The Pearson correlation is for test relationship between independent and dependent variables. This range should be -1 to +1 in all our results in the within the range, and also we can accept the all results. Here, regression. Regression is a numerical tool to study relationship between variables. According to the model R value, indicate positive linear relationship between overall in these variables. This is our regression equation we developed. According to the beta values, we derived this coefficient table. Then this indicate changing one unit of independent variable, how much to affect on risk mitigation, keeping other variables constant. Discussion. Mainly focus in this research to analyze the relationship between these channels. In aircraft engineering aspects, have to concern especially on initial training for every technician and engineers, and continuous the safety assurance and recurrent training also important. Most of organizations have lack of budget allocation for training resource, but we, according to our findings, it is essential thing. Conclusion. Language proficiency of employee develop innovative training system. Also, informally conduct safety audit, also essential for safety. And continuous training is very important to the every employees and directly affect to the safety. Further research can be carried out, considered qualitative data gathered through interviews and focus group discussions. Acknowledgement. We would like to express our deepest appreciation to our supervisor, Dr. WTS Rodrigo, who motivate, advise and encourage us regarding to our research. And also we would like to extend our sincere gratitude to Department of Aeronautical Engineering and all the academic and non-academic personnel who have helped us along. Thank you.
Okay. Once again, thank you, Mr. Bandara and Samarakoon. Regarding training, they were discussed about three main training: the initial training, and the continuation training, and the training resources available for the training. So if you have any questions regarding any thing relevant to the subject, you can ask now.
Sir, actually this is not a question that I'm going to ask, but as a supervisor, once they were conducting the two presentations, I understood that there are certain areas that which needs further clarification. So first I would like to congratulate them on their two researchers, because this was based on their final year project. Because in aircraft maintenance engineering, we cover a subject which is called aviation safety management systems, which is very important, because which talks about the equilibrium between safety and productivity in aviation. Because wherever you increase safety, the productivity is compensated. Wherever you increase productivity, the safety is compensated. So in order to manage that, we have the concept of safety management system. So in the normal context of safety management system, most of the topics are already covered. If you look at safety risk management and safety assurance, it has been researched continuously. So therefore, I basically inspired students to research more on the promotion aspect, which is being divided into two areas, that is the training and the communication aspect. Because we see as the practicing engineers, there is two areas where we are lagging a lot. So their first paper was mainly focused towards the training, the communication aspect. So there we have, through an empirical analysis, we were able to identify there are significant problems available in the industry. So we need to take action. For example, like the effective communication is not there and we need to promote them, especially in the military context. And then we moved on to the technical aspect, technical training, where because of the cost involved, sometimes the organizations tend to pay less concern on the training aspect, which has adverse and a sort of snowballing effect on the end result of the safety. So I think those are the main two findings that we were able to find. And the reason why they went for two papers is that if you have to combine training and communication, that would give an odd shape for research. So that's why they were mainly looking at the two components separately. So I thought as the supervisor, it's my duty to enlighten the audience. Otherwise there might be concerns like why two papers are being presented by the same two authors. So I congratulate you and thank you very much.
Thank you very much, sir.
Thank you. Any clarifications or any questions? If you don't have any questions, I think now time to sum up this session. Today we discussed almost 4 topics related to the aircraft maintenance industry. Maintenance. First one, thermographic inspection, system for surface scouting, defects on aircraft fuselage. That is innovative subjects and innovative topic you are going to do, and I hope that you will continue and we can see the results in future. So that is new thing. If you can innovate that product, that is very helpful. We know that how cost will involve for the NDT inspection in Sri Lanka, even Air Force. So that is a very effective topic, and thank you very much. So I hope that will continue. Second one, that is basically aerodynamics, more theoretical part, estimation of lift hysteresis of airfoil in a low speed airflow. That is again the relevant topics regarding the much of them can't do in outside this kind of topics, because you have the wind tunnel and other facilities you can do in KDU. So that's why that is also very good thing related to the UAVs. That is very common topic in Sri Lanka in aviation industry. Third topic is, as clearly mentioned Dr. Tusita, that it very rare to researchers have done in Sri Lankan aviation industry regarding technical communications and training. So those two topics are very rare and very important, but much of the aviation even engineers or technicians, they are not given due recognition to that two topics. But when you got some issues or problem, then they are highlighting the importance of these two topics. So that is also another good two researchers done by the Mr. Bandara and Mr. Samarakoon. So thank you very much. Once again, if you have any questions regarding any subject, you have 1 minute, or otherwise we can conclude this session. If you want to tell anything regarding your topics? No? So then once again, thank you very much. All the evaluators, senior professors, senior lecturers, head of the Department of Aeronautical Engineering. And once again, I would like to thank Vice Chancellor and the Dean Faculty of Engineering and the head of the Department of Aeronautical Engineering and all the staff members and non-academic staff who invited me to chair this session. Thank you very much, and I wish you all the very best for the authors and all the undergraduates who are studying in KDU. Thank you very much.
Thank you, sir. Ladies and gentlemen, now we have come to the end of the technical session, which was really interesting. Now, I would like to invite Air Vice Marshal LMSK Leelaratne, retired, accompanied by Dean, Faculty of Engineering, Captain S.U. Dhammika, retired, to award certificates to the authors who presented in the session. Ms. WPMY Thilakarathna and Mr. A.A. Ziyard. Cadet Corporal W.A.R.D. Jayathilake. Mr. KMGMWB Samarakoon. Mr. SCM Bandara. Thank you, everyone. Air Vice Marshal LMSK Leelaratne, sir, I would like to kindly request you to remain on stage. Also, I would like to invite Major General Adipa Thilakarathna, retired, accompanied by Wing Commander UDLP Wijesinha, to present the certificate and token of appreciation to the chairman. Thank you, sir. Thank you, sir. On behalf of the organizing committee, I would like to thank Air Vice Marshal LMSK Leelaratne, sir, for chairing this session. We would also like to thank our presenters for their kind contribution in making this event a success. With that, we conclude the second technical session of the day and hope you all have a pleasant day. Thank you.
Recording.